Welcome back to Chapter 1.4, The Law of Large Numbers and the Central Limit Theorem, Part 10 of 10, the finale. In Part 9, we laid out the hierarchy from slow convergence to outright failure. Now we watch the bell refuse to form, lay out what Devon should do, and look ahead to where the two laws carry us next. The simulation that makes this unforgettable is the experiment from Part 6, rerun with the fat-tailed population in place of the exponential. Devon uses a student's t at 3 degrees of freedom, heavy enough to misbehave, but with a finite variance. Compare the picture to Priya's. With the exponential, n equals 30 already matched the bell. Here, at n equals 30, the histogram is far too peaked in the middle and too heavy in the tails because the occasional monster draw keeps throwing the sample mean far out. By n equals 100, it is better but still off. You have to push n into the thousands before the histogram finally agrees with the dashed normal curve. Same theorem, same standardization, drastically slower convergence. The only thing that changed is the weight in the tails. For the pathological case, swap in the Cauchy and rerun the running mean plot. The running average jumps around forever, never converging. That is the law of large numbers failing in front of you. The point is not to make Devon give up. It is to make him honest about what his tools can promise. The practical responses, all of which you will meet later in the book, are these. Report that returns are fat-tailed and quantify it, rather than assuming normality. Lean on the median or other robust summaries that are not hostage to a single monster day. Use far larger samples before trusting a normal approximation. And when he builds standard errors, use ones that do not silently assume thin tails. The single most valuable habit is the cheapest. Before trusting any average, plot the data and look at the tails. If the raw returns have fat tails or outliers that dwarf the bulk, treat every central limit theorem-based claim as provisional until you check whether the bell actually forms. You now have the two pillars. The law of large numbers guarantees that with enough honest data, the sample mean lands on the truth. The central limit theorem guarantees that the misses, rescaled by sigma over the square root of n, follow the standard normal bell, provided the data are not so fat-tailed that the bell never forms. Hold on to the standardized quantity because the next chapter is built on it. In Chapter 1.5, we confront what we have been quietly cheating on. In real life, we do not know sigma and must estimate it from the same sample. Replacing the true sigma with an estimate, sigma hat turns that normal into a slightly fatter-tailed cousin, the student's t-distribution, the very family we just used to break the central limit theorem, and from it we derive the t-test and the confidence interval. To summarize this finale, with a fat-tailed student's t-population, the bell needs n in the thousands rather than 30, and with the Cauchy, the running mean never settles, and the law of large numbers fails outright. Devon's honest response is to plot the tails, quantify the fat-tailedness, lean on robust summaries like the median, and use far larger samples. You now hold the two pillars and the standardized quantity at the center of everything. In the next chapter, we estimate sigma from the sample, which turns our normal into the student's t-distribution, from which we build the t-test and the confidence interval. That is the law of large numbers and the central limit theorem, shown not asserted. Well done.